right, times the determinant of that, right? Which would be this times this minus this times this. Okay, I'm going to write that out. Partial y with respect to v, partial z with respect to w minus partial z with respect to v, partial y with respect to w. Let's double check this. Partial x with respect to u, then it's this times this. We got to make sure everything's right. Minus this times that. Yes? Okay. Minus, because when you do determinants, you alternate signs. Minus, now we do this one. Partial x with respect to v, and then the determinant of these four right here. So partial y with respect to u times partial z with respect to w. Partial y with respect to u, partial z with respect to w, minus now this one times this one. Or you can do it the other way around, doesn't matter. Partial z with respect to u, partial y with respect to w. Again, I'm going to check. Y with respect to u, z with respect to w, z with respect to u, y with respect to w. One more. And I think I'm still out of room here. Okay, yeah, take your time. I'm connected. I'll start it. Okay, partial x with respect to w. And then the determinant, so partial y with respect to u, partial z with respect to v, minus partial z with respect to u, partial y with respect to v. I think we've got it. I think we got it all here. Let's see if Word ever opened up for me. Yeah. There we go. All right. Okay. Now it's time to plug and chug, right? Plug and chug. Here we go. This is going to be nasty. Can I, let me move it up here. I want to put it up here. Okay. Yes. What?
Maybe do a u relax itself.
Do a what?
Instead of doing all the partials, let u equal to a partial, as opposed to writing it all at a time.
But I see what you're saying, but I need it to all be next to it because a bunch of trig stuff's going to happen. Things are going to be great. Yes.
Can we just eliminate the terms that have?
You want to eliminate the one that has 0 in it?
Yeah, 0.
Which one has 0?
The first and third.
Which one? That's the one with ZV. That one right there? You want to get rid of that? Everyone okay with that? That's gone, and then
I think the first one of that last group.
this one right here. So what we're doing here, oh wait, no.
One of the third group.
See. This one's here,
That one. Yeah, that one.
that one. ZV, that one right here. Those are gone. I'm okay with that.
Yeah, that.
It's not the way I do it, but there's nothing wrong with that, right? You still get there. Okay, so now let's do this. Partial x with respect to u. Cosine v, sine w. Okay, times, now I don't need parentheses because this term's not here, right? So I just need these two multiplied next to it. So partial y with respect to v, u cosine v, sine w. And then I still need partial z with respect to w, which is times negative u sine w. That's what that is. That's these three multiplied. Now, over here, this one's going to be a little bit different. Minus, okay, partial x with respect to v is this one. So that's going to be a double minus, isn't it? So minus u sine v sine w. Okay, that's just this right here. And then I'm going to go ahead and do a parenthesis. Partial y with respect to u, sine v sine w. And then times partial z with respect to w, negative u sine w. So I've done this, and this. I had a minus sign now. And then partial z with respect to u cosine w. Got this. Partial y with respect to w. U times u. I'm going to keep going this way. Sine v cosine w. All right. So now I've got this. Close the parenthesis. And then partial x with respect to w is here, and this is a plus. So u cosine v cosine w. Now I've done this. I don't have to do that, right? But now a negative, right? That negative. So is it all right if I just change that to a minus right there, everyone? Instead, because this is going to multiply through times two different factors, and all of them will be, well, the negative will carry through, so make that a minus. Partial z with respect to u, cosine w. One more. Partial y with respect to v. U cosine v sine w. Okay, I don't want to erase this because I'm afraid to erase it in case y'all messed up. I won't have proof. Okay. Somehow that's going to simplify down. But I think you'll start to see it's going to come together pretty nice here if you did everything right. See, I've like turned it on you now. So let's look at. Yeah, exactly. Exactly. Here, let's do those together. Be careful. This is multiplication of a negative that is not a minus sign, right? So when I put all those together, let me do the u's first. I get a negative u squared. Right? I've got negative u squared. Those are gone. Okay, cosine v, so that's a cosine squared v. Cosine squared v, right? Gone, gone. Sine w, sine w, sine w. Sine cubed. Okay, I'm done with this first piece. Now let's move to the next piece. I'm multiplying all of this together, aren't I? These two together become positive, but then I have a negative here. So this is going to be a minus, right? How many u's here? 2, so u squared. Got my u's. Okay, let's deal with the v stuff first. Sine squared v. Okay. Sine cubed w. Hey, I've seen that before. All right, and then the last one. Let me see. Oh, no, there's not a last one. Oh, shit. What did I just do? I just missed. Yeah, I've got it. That was just these two together, right? I should have pointed that out here. This is this to this, right? Now I still have to go what? That to that one. Sorry, so let's change this to a plus because it's just annoying. That's a plus. This term is minus, right? Okay, now when I go from here to there, I'm going to get minus again, right?
No. Yes. You have a negative.
No, I'm treating this like a plus.
Okay, yes.
This is a plus. A minus minus is a plus. Let me just erase this. Let me go plus here, like that, okay? So when we went from here to here, that gave us a negative. That's this. Now go from here to here. That's a minus, so we'll have negative. How many u's? So u squared again. What next? Let's do the v's. So sine squared v. What else? Oh, look, the two cosines right here. They're the same thing, right? Cosine squared w, and then we have how many sine w's? Just one? All right, that should be it. I hope. We'll find out here in a minute. Right? And then this last one over here, it's a minus. It's a u squared. I've got cosine v squared. And then cosine w squared. And a sine w. Yeah? Do y'all see it yet? Yeah? See what's going to happen? So look at these first two terms right here. And let's pull a GCF out. Greatest common factor. What do they both have in common? Negative u squared, sine cubed w. And what were you left with when you did that? Cosine squared v plus sine squared v, which will turn into a 1. And then on these two terms, let's pull out GCF here. They both have a minus u squared, right? What else do they have in common? Sine w and a cosine squared w, right? So if I pull the u squared, I pull the sine w, and I pull the cosine squared w, I'll be left with sine squared v minus cosine squared v. Plus. We pulled the negative out. Those turn into 1s, right? 1 here, 1 here. So now all we have is minus u squared sine cubed w minus u squared sine w cosine squared w. And factor GCF again. Minus u squared sine w, and what are you left with? Sine squared w plus cosine squared w. Right? If you pull that GCF out, and the sine squared w, cosine squared w added together is 1, and that leaves you with this. Right? Because that turns into a 1. Now, we're supposed to take the absolute value, right? I left that out. Do it here at the end. The absolute value of that would give us u squared sine w. And remember, what was u? U was rho, so rho squared, and then w was phi. So rho squared sine phi. There it is. Yeah. That's pretty cool, yeah? I mean, that's a lot of algebra, right? A lot of algebra, but it turns out to be something nice at the end, I think, right? All right, so that's how the Jacobian determinant works. That's why we get the r with polar. That's why we get rho squared sine phi. Let's now look at a problem where we're going to convert to another system that is not one of these, all right?
Did you say it's two-dimensional?
Is what?
Did you say it's two-dimensional,
Is what two-dimensional?
this problem?
The one we're about to do? What? The one we're about to do? Yes, it is. You'll see right now.
I don't want to do the triple, the 3x3 matrix.
What made that just kind of tedious right now is because we were doing it for very complicated conversions. I mean, these are not easy. These are not just simple conversions. This is sines and cosines mixed, right? So our derivatives were a little bit weird. Take a moment to look at that. I only have 20 minutes, 18 minutes. Let's see if we can do this problem in 18 minutes.
do not use u.
So look, we have this double integral, not triple, double integral over some region D of 4x plus 8y with respect to area, and then I tell you about D, the region we're integrating over. And what we're being told to do is to change our variables and create these transitions into a new variable. Now, y, hopefully it's going to be better, right, when we convert it. That's the y. How would you come up with these on your own? That's a more complicated question I'm not ready to address today. We will address that next class, all right? For today, for this last problem, only problem we're going to do, I'm going to give you the actual conversion. But I want us to see why we would even want to convert first. So I'd like to draw the region D first. And to draw the region D, I'm just going to plot the vertices of this parallelogram. So negative 1, 3 is a point right there. 1, negative 3, point right here. 3, negative 1, somewhere around here. And 1, 5 is somewhere up here, like this. It's not a great picture, but you could plot the points more accurately, right? And then I'm going to draw the parallelogram that's connected here. Now, I'm supposed to integrate over that region. The problem with that region is that it's not a very good type 1 region, right? You don't have like your x between two constants and your y between two functions of x. If you looked at it as type 1, you'd have to break it up into different pieces. You'd have to look like maybe just from here to here first, and then you go like, well, I don't know, are these lined up? Yeah, they are. Then from here to here. So you'd have to break it into two double integrals. Or same thing if you did type 2. You'd have to break it up. And it's definitely not a polar region, right? So you wouldn't want to do polar. So maybe there's a way that we can convert this over, change the variable so that our new region is better than that doesn't require the breaking up. So I'm going to do this conversion right here, right? So what I'd like us to do is let's label these points. This is the point 1, negative 3. This is the point 3, negative 1. This is the point 1, 5. And this is the point negative 1, 3. All right, I'm about to say something very important, all right? It's subtle, but it's important. These conversions from xy over to uv, these transformations are linear, meaning the u here is to the first power, the v is to the first power, v is to the first power, u. These are linear transformations. And I know some of you are taking college algebra. I mean, linear algebra. I'm ready for the summer, I guess. No, I'm ready for spring. We still have so much to do. Like chapter 13 is like on the horizon, and that's like the monster chapter. So I need a good weekend this weekend. Some of you are taking linear algebra, right? And should know that when you have a linear transformation, that linear transformations take lines to lines. So any line in one space gets mapped to a line in the other space if it's a linear transformation. If it's not, if it's some nonlinear, then you're not guaranteed that that's going to happen. So for those of you who are not taking linear algebra, that's okay. I'm telling you, notice that these are linear transformations because the powers of the variables are ones, and that assures you that the transformation is going to take this line to a new line in a new space. And that line segment is going to go to another line, and that line is going to go to another line. And points are going to go to points, all right? So what I'm going to do to draw the new space is I'm going to just map these 4 points over to the new space and then connect them with straight lines. So let's take a look at that first point on top left. Let's take a look at that point, negative 1, 3. That gets sent to a new space through the transformation. This is the x and this is the y, and the question is, what happens over here? What does u become and what does v become, right? So how would you do that? How could you do that? If I give you x and y, can you give me u and v? What do you think? If I tell you that that x is -1, right? And I tell you that that y is 3, then you have two equations with two unknown variables, and you could solve for them, couldn't you? And I could do that for each of the 4 points. That's a little inefficient, though, because we'd have to do 4 different systems of equations, right? Like 4 different times. I don't want to do that. So what I'm going to do is try and convert over first. I'm going to try and get an equation for u, and I'm going to try and get an equation for v. Let me do it this way. I need that picture still. So let me write down those equations right here so I can work with them. X is 1/4 u plus v. And then y is 1/4 v minus 3u. Let's work with this one. I'm going to multiply both sides by 4. And over here, I'm going to multiply both sides by 4. That just killed off the fraction, right? I'm going to solve this equation for v and plug that in right there. So solve that for v, subtract u on both sides. Now take that answer, stick it right there. So you get 4y equals, what, 4x minus u minus 3u. Right, that's me just taking this right there and replacing it right there, which puts it right there. Now, I can say 4y equals 4x minus 4u. Yeah, let's get rid of the 4's. Divide by 4 is fine. What do you think I'm going to do with that? Solve for u. Solve for u. So if I solve for u, I get this. Move the u to the left, move the y to the right. And what am I going to do with that? Put that back into the other one, right? So take this answer, plug it back in here for that u right there. So you get 4x minus parentheses x minus y equals v, which is 3x plus y equals v. I have an equation for v in terms of x and y, don't I? And now can I say what, oh, I have the other one too, sorry. This was the other equation right there. I have equation for u and for v. Even though that was a little tedious, that's better than having to solve 4 different systems, like plugging in the 1 there and the 3 there, solving that system, and then doing it for each of the 4 points. I think that's a little bit more efficient. Let me write that down. U is equal to x minus y, and v is equal to 3x plus y. All that work to get that. How are we doing? 9 minutes? I just erased everything I need. No, I have the points. I have the points right here. So, all right. So where does the point -1, 3 go to? So let's plug in to get u. I plug in -1 right here, and then 3 right here. What does that give me? -4, comma. Now to get v, right, the v coordinate, I'm going to plug in here -1, and then here 3, which gives you 0. Okay, so in the xy coordinate system, this was the point I was trying to, that was one of the vertices of my parallelogram. And when I take it through this transformation to this new variable, these new variables, right, that's the point in the uv plane, right? So we start out in the xy plane. We're doing some transformation. Capital T takes us into some new plane, the uv plane. And I know that that point went to that point. Let's do the next point. Let's go with 1, -3. So with that transformation, so do the same thing, right? U would be 1 take away negative 3. 1 take away negative 3 is 4, isn't it? 4. And then the V is 3 times 1, then plus negative 3, so that's 0.
That makes sense.
And then we have, let's see, 3 negative 1. So let's start with this one. 3 minus negative 1. 3 minus negative 1, so 4. No, minus negative, so plus.
No, yeah.
And then now 3 times 3, 3 times 3, and then plus negative 1, that should be 8. 4, 8. And then one more. Negative 4, 8. Y'all got that? So we saw earlier that our plane, we had this like parallelogram that looked like that, right? Now when we do this change of variable, right, this becomes in our UV plane this new region, and it looks like this. This is the U and the V. It's the point 4, 0, right there. Negative 4, 0, or yeah, negative 4, 0. 4, 8, so up here, and negative 4, 8. And we have a box, or rectangle. And I'd much rather integrate over a rectangle than over a parallelogram, because I don't have to break anything up. Now you might argue that by this point in time, he probably could have broken it up and been done. But this is your first example, just to show you the value of it, okay? This is not a good example to convince you to use it, all right? Questions so far? I've got a few more minutes. I need to finish the problem up. Because what I've done right now is I've taken a look at what this new region looks like, right? So now we got to convert this all over. We've got to convert this integral over, right? So instead of going integral over D, let's call this S, because that's what I notated in the book, or in the notes. We are now going to be integrating over S, right? Over S. And I need to take our function, right? Our function in here that we're integrating, I need to do change of variables on that. So instead of 4 times x, I'm doing 4 times that, right? So I'm going to do 4 times 1/4 u plus v, right? That's 4x. Then what is the plus 8y? Plus 8 times y, but y was 1/4 times v minus 3u. Jacobian. This is the part right now that we need to understand. Like everything we've done so far was just moving everything over to x, from x and y to u and v. But if we do a change of variable, you have to include the Jacobian determinant right here, which we have not done yet, right? We have not computed the Jacobian determinant. We got to do that now. And then we'll put that here, and then we'll go dA, and then we can set up our limits of integration. Those will be easy, right? Negative 4 to 4, 0 to 8, right? So I need Jacobian now. So for the Jacobian, it's going to be the absolute value of partial x with respect to u, partial y with respect to v, minus partial x with respect to v times partial y with respect to u. So I'm using the formula that I put up on the board earlier. I'm using the one out of the notes right there. I'm using this one right here. Okay? That's what because I'm in two-dimensional space, I can do this. And do we have our formulas for x and y? They're right there, right? So we should be able to take partials of those.
Not that.
So this is the partial of x with respect to u. So you're looking at x as a function of u and v, as opposed to this. Here, You could still do a partial, but you need to move things around. You need x in terms of u and v. Here, x would be in terms of u and y. So don't use those. We use those to move our points over. It's a mess. Okay, what is this? 1/4. Right? Because the 1/4, just ignore it. Take derivative of u plus v with respect to u. It's just 1. So you get 1/4. Partial of y with respect to v. 1/4 as well. Minus partial of x with respect to v. 1/4. And then partial of y with respect to u. -3/4. Absolute value of this. If you put this together, this is 1/16 plus 3/16. Multiplying negative is positive. That's 4/16. Absolute value of 4/16 is 1/4. See, this was a linear transformation. So there was no like twisting or curving of anything. Everything, lines went to lines. And because it was a linear transformation, our Jacobian determinant is a scalar. It's not like the polar conversion we had r, right? R is not a scalar. And that's because when you go from Cartesian to polar, there's like a turning and twisting of things, right? Things get manipulated, but not linearly. So your Jacobian determinant will be nonlinear, or non-scalar. Same with spherical. When you go from Cartesian to spherical, again, it's not lines to lines, right? So because of that, our Jacobian for spherical is some complicated rho squared sine phi. But if you go from one space to another through linear transformations, you should expect that this is a number that just like shrinks, scales, that's it. All right, so let's tack that on right here, times 1/4 dA with respect to area. I got 30 seconds and I can finish setting up the integral. So now I'm going to go integral from, this is the variable, what variable is this? That's my u, right? So -4 to 4, and then this is my up and down, right? 0 to 8. And then we never clean this up, but this is actually pretty nice because that distributes there, the 1/4 and 4 are gone. So that's just u plus v. And then this goes here and becomes a 2. So 2v minus 6u times 1/4 times dv du. There you go. There's a little bit more you can do here. Put your u's together, put your v's together. There's your integral. The beauty of that integral, if there's a beauty, it's arguable if that's beauty or not, but this is easier to evaluate now, right? This is a much easier integral in terms of our limits of integration. There's no breaking things up. There's no upper function, lower function. Okay,